Thank you, Fernando. And I want to thank you for a great conference and also the organizers. Sorry for my voice. I don't have corona, don't worry. This is a post-corona effect. I had it 3 weeks ago. And some people would call this long COVID, but I don't think it is. So that's a question I want to ask. And I want to say this is work in progress and published work with amazing collaborators, which I would like to thank. All right, so let me start right away. Wormholes, Euclidean wormholes, especially axion wormholes, have appeared in the Swampland discussions a lot before. So let me just remind you of this a little bit before we can really start, okay? So I think one of the first papers that discussed them was this paper by the Stanford group. And this was in the context of breaking axion shift symmetries and by a quantum gravity effect, which would be the wormhole as a gravitational insult. Okay, this idea was revised really when the Swampland took off. And wormholes were recognized as objects predicted by the axionic version of the weak gravity conjecture. And then there was this whole link with large field inflation, whether axion decay constants cannot be too large, etc. Okay. Interestingly, also confusingly, the argument is that Euclidean wormholes are required for the Swampland because they need to break a global symmetry. A similar argument shows that they are actually in the Swampland. They shouldn't be there because they would actually, if they are there, if they correspond to baby universe nucleation, then the argument of Jake, who is here, and Komu Pafa, is that they would actually give you a global -1 form symmetry. Okay, so this is a confusing statement. Finally, one of the last things that happen in the context of the Swampland is you say, okay, we assume they're good objects. What happened is that the weak gravity conjecture got refined. Similar, like you have a weak gravity conjecture for microscopic objects and macroscopic objects. Think of large black holes and then derivative corrections to them. Something similar has been done, which I will also explain, okay? But my question is, this is a confusing state of affairs. Wormholes are needed for the Swampland, but wormholes are in the Swampland. What now? Okay. And I cannot answer it, but I will end by saying the pros and the cons, right? So before I do, let me also remind you very quickly what are Euclidean wormholes, a la Coleman, Giddings, and Strominger, in case you don't know this. So assume I have a matter Lagrangian, which is a pure axion. It's actually very convenient, especially if you go to Euclidean signature to dualize it into a p-form. So in 4 dimensions, this would be a 3-form field strength. And then you look for a gravitational Euclidean instanton, and you take one which has all the symmetry, so it's perfectly radially symmetric. And what is going to happen is that the 3-form flux is going to fill the sphere. And the intuition is obvious. When you do that, you can actually get a wormhole because the sphere cannot collapse due to the flux that's inside the sphere. Okay, what would be a wormhole in such a metric? Take F equal to 1. It would mean that the scale factor is that of, say, flat space or ADS, whatever. It shrinks. And at some point where it wants to vanish, it actually stays finite, and then it opens up again. That's a Euclidean wormhole geometry. The metric is very explicit, but it's much shorter to fit on a page. If you write a metric in another frame, where you take the gauge where this is just equal to tau squared, and then this function is non-trivial, I just show it because to show you that it's a very simple solution. But in this frame, it's difficult for you to see that it's a wormhole, okay? But I just want to show it. So as you can see, I actually allow the possibility that there's also a negative cosmological constant because I want to confront this with holography. Right. What's important about the solution is that it's everywhere regular. When something is everywhere regular, it's not carrying any monopole charge. So you should think of the full wormhole as some kind of a dipole. There's, from this angle, there would be minus n units of charge. From this angle, there would be plus n units of charge. You can also very quickly calculate This object has a finite action. This is why it's an instanton. And the action is proportional to the charge. All right. This has a huge history. Also prior to string theory. And I think it's very important to learn this history because now we have string theory in holography and we should go back to these old questions. And I can really advise you to read this review if you're interested. These authors really put an effort in trying to put everything together, okay? Also the stuff before the advent of string theory. Good, so let me just mention the most important things before string theory came about. And is that these gentlemen have given an interpretation. Well, it was mainly common, but have given an interpretation to these wormholes, right? And to do that, maybe let us just look at this figure. And I'm looking at half the wormhole, all right? So this is Euclidean time. And as I evolve it forward, you see that I have space, but then I have an extra 3 ball here, right? I mean, this is very quick, just a picture, but still, right? So especially when you continue to Lorentzian signature, there's sort of a picture that you can think of the full wormhole as describing both the emission of a baby universe and the absorption of a universe, of a baby universe. So half of the wormhole is either emission or absorption, and the full wormhole is the total process, okay? What is this baby universe doing? What is it carrying? Well, it's exactly carrying axion charge. So imagine I'm in my universe and I do experiments to measure axion charge. This instanton is telling me that suddenly this value can go up and down, okay? Which is good because axion charge comes from a global shift symmetry. We're saying this cannot exist, so it should be violated. So to an observer, I should detect a violation of axion charge. It should not be conserved. It's exactly what the wormhole is doing for you, all right? And at the time, people say, oh, this is great. This to an observer looks like apparent non-unitarity, but it really is not in the full universe. So this was the excitement at the time. But when I look at wormholes that I glue in the same space-time, this is a very closely related thing. Then the solution is approximately the same, but of course there is some non-zero force between these two wormhole ends, but you ignore it, similar to like instanton gas approximations. So these things exist as well, but they are also puzzling. And this was Coleman's puzzle, which he claimed to have solved. So imagine these things exist, you would think that your effective Lagrangian now is supplemented with bilocal operators, right? Because I have 2 endpoints. So this would violate some form of locality. But Coleman realized, and this is a trivial trick, you can easily calculate this. He says, but this is not entirely true. What I can do is I can replace, if I take an effective action, I insert bilocal operators. I can trade it for having an action which doesn't have no localities, but at the expense of introducing new variables, which are just random with some Gaussian weighted function. Okay, this is a very quick formal path integral trick. It takes you a few lines to derive. The bottom line is, by defining some arbitrary variables, which are called Coleman alpha parameters, I can rewrite this as an effective action, which doesn't have bilocal operators, but there are coupling constants in nature that are arbitrary. They sit in some ensemble. That's the price to pay, right? So this is how we get to ensembles. Okay, today we have string theory. Can we test these ideas? Well, if you want to do that, you need to have a string theory embedding. And this is a topic with some history, but surprisingly not much. I've always been confused why not more people have worked on this, all right? So there are 2 ways to try to find axion wormholes in string theory. The first one is you say, look, first of all, we know that axions don't appear in string theory for free. They pair up with axions. In all examples we know, all right? So what we can do is we can try to therefore look for a multi-field system of axions and saxions. So I have a general kinetic term, and there are true moduli, all right? So as they flow, the vacuum energy remains 0 or negative or positive. It remains constant. Okay. Question is, can I find such Lagrangians as consistent truncations in string theory? Second option is more what a phenomenologist would do. If we really believe axions exist, then this axion is probably very heavy. So a phenomenological Lagrangian would be of this kind. Here is this axion. Here is its potential. This axion is just in a very sharp potential because it has a high mass. And here is the axion. Okay, so I can try to look for these two kind of things. What I'm going to do is I'm going to do this. I'm first going to start with this because this requires a phenomenological Lagrangian. So I would have to do KKLT, large volume scenario. It's much more complicated. This is great. It's formal. I can use it for holography. Okay. So let me try to get this. Before I get it, I want to already show you what are the solutions because we have a few examples already. So hold on. I'm just going to quickly tell you about solutions and then how you get them from string theory. So imagine I have some general Lagrangian like this, which is a consistent truncation. Then you can see it. The geodesics, the scalar fields will trace out geodesics on the sigma model, right? And you can see that using the harmonic map. To make a long story short, there is some kind of a parametrization of the radial variable, which makes it the radial variable into a harmonic. And then you can nicely show that the equations of motion for the scalar fields are geodesics. So they're characterized by some constant, which is a geodesic velocity. It's a number. Here comes the catch. This number doesn't need to be positive. If I'm in Euclidean signature, an axion has the wrong sign of the kinetic term in the scalar formulation. So I'm looking at a sigma model with an indefinite signature. C can be 0, negative, or positive. All right. And the metric doesn't need to know about the details of the sigma model. This is the general metric in d dimensions. So this number C appears, right? Okay, so one of the important themes of this talk is, okay, we know that the scalar fields are geodesics. And I have a problem now because, okay, I'm going to analyze the solutions. I'm going to analyze it in string theory, but I need to know something. What if these geodesics have a long length? Well, there's a distance conjecture. How does it work in Euclidean signature? Because the distance can be 0, negative, or positive. To my knowledge, there is no formulation of the distance conjecture for the Euclidean theories, and I think it's an open problem. And I invite people to think about this. So if the solution is negative, C equals negative, that's a wormhole. How to understand this? This means that the scalar field in the sigma model that is contributing the most are the ones with a negative kinetic term, the axions. So it's like Coleman's or the Strominger-Giddings wormhole. There are solutions which exactly have C equal to 0, and there are solutions with C equal positive. I will not discuss those guys. They are not understood. And I have some papers on it, but I'm not going to explain. These ones you all know. Okay, the geodesics are light-like, but they're actually supersymmetric instantons. All your supersymmetric instantons that you know, they are of this kind. Take Euclidean D3 braid. You can always rewrite it in this language, okay? But let me discuss the wormholes. So bottom line is, with the extra appearance of these axions, I can actually call these things over extremal, extremal, and under extremal. That notion doesn't exist if I only have an axiom. So how does that come about? Very quickly. There's lots of literature on this. I'm just going to make it very simple for you. We're going to use a particle instanton map. So take a particle or a black hole and reduce it over time to an instanton. If you do that, the extra dimension gives you this axion, the radion, and the gauge potential, like under which the black hole is charged, gives you this, the axion, okay? And then this would be the kinetic term. This is the simplest example. You can just dimensional reduce Risen-Nordstrom black hole, you get instantons of this kind, okay? Then the wormholes would live to the over-extremal Risen instanton, and the sub-extremal one would live to this weird solution. All right, so the on-shell actions are of this nature. This is the dilaton, the axion at infinity. So what you see, now you probably understand the words over-extremal, under-extremal, extremal as well. Because if C equals 0, then the ratio between the action and the charge is BPS. When C is bigger, the action is larger than the charge. When C is negative for a wormhole, it's clearly over extreme, right? There are many other checks for this picture that this is correct. Like when C equals 0, you can extend the solution to a multi-center solution. So there's clearly no Euclidean force at work, just like for supersymmetric solutions. You can use probe D-brane arguments to verify this picture, okay? Over-extremal black holes are unphysical. Not over-extremal particles. What about over-extremal instantons? Okay, there's no naked singularity to warn us. So the question I'm asking again, is it in the swampland or not? You can be confused how an over-extremal black hole can reduce to a regular instanton. I'll explain this, okay? So the string theory embedding. I promised you whether string theory can maybe help us. So let's look at it. Let's try to get this Lagrangian. So one example is type 2b on S5. I get this Lagrangian, where beta equal to 2. And epsilon is -1 in Euclidean signature. Okay, so what do I have? I have the supersymmetric solution, C equals 0. That's the D instanton in ADS5 cos S5. We understand it. The wormhole is singular. How? The geometry is perfectly smooth. But if you look at the scalar fields, I wrote the general expression. You don't need to look at the details, but we can just eyeball this. E to the phi goes like a sine. What happens is that the sign at some point goes through 0, and I cannot evade that point within the wormhole geometry. That's what happens. So the solution, the scalar fields are singular, right? But this depends on the number beta. When beta is small enough, I still have the sign solution, but I can make sure that the sign remains positive from the left-hand side of the wormhole to the right-hand side of the wormhole. So the question is, can I do string compactifications where I get beta small enough? All right. What I would need is beta squared smaller than 3/2. So this is a challenge to anybody doing compactifications. Can we get it? And then you can ask yourself, okay, what about the general sigma model? This was answered in this paper. Let me not go through the details. Let me just mention how it works for the general sigma model. That is an argument using Einstein equations that the geodesic length will always be given by this formula. By the way, you see, the geodesic is long. Well, long. It's definitely super Planckian in distance, and this is the distance, right? These are Planckian units. And what we want the smoothness is the same as saying that this time, like geodesics, should at least have this length. But this depends on the sigma model, whether that is possible. All right. So we need to find sigma models which can support long enough geodesics. By the way, this is already, as I said again, not sounding great from the point of view of the distance conjecture. So imagine I can find such a sigma model. I would still like to leave my solution because I would be worried. And that's what I'm doing in this project with Gary and Greg. And let me just tell you what is known. So there's one explicit ADS CFT embedding, which we found a long time ago in ADS5 cos S5 over ZK, when K is large enough. And you get beta equal to 1. But the lift of these solutions we cannot carry out because it's an orbifold, right? So, I mean, to some extent you can understand it, but not completely. So this is why we're doing something else. By the way, I just want to tell you that if I put K large, this geodesic length diverges in Planck units. So you can say, oh, this is bad for the distance conjecture. What is funny is that the geodesic length is always the same in species scale units. Okay, so I think that it's kind of good from the point of view of the distance conjecture. So what we do Minkowski models because we really want to lift to 10D. And it was already pointed out in 2004 in a paper that everybody seems to ignore that for a general Calabi-Yau solution supports Euclidean wormholes in flat space. And that's because universal hypermultiplet has a beta, which is equal to 1. So it works. So what we did with Gary is we lifted the solution to 10 dimensions to understand it. Why? Not only because of the distance conjecture, we got worried whether maybe the Sugra is lying to us and it's not a good solution. There's a paradox because we know that for the Calabi-Yau compactifications, the extremal SUSY solutions, we know them. I told you, it's like a Euclidean D3 wrapping a calibrated cycle. But this is problematic because the Euclidean branes we know they do not have over-extremal partners, right? So how is this ever possible? So that's why we wanted to lift the solution and just look at it, right? So here is a lift. You can eyeball it. We did. You don't have to do it. You can just look at this picture, okay? So this is in type 2A. We also have type 2B solutions. So what you have in type 2A, you see a bunch of Euclidean D2s wrapping 3 cycles on the Calabi-Yau. Yep. But what happens, the only way to get a smooth wormhole is if you put all of these stacks together and then take the over-extremal limit. You see, in this case, there is no paradox because there is no Lorentzian picture anymore. Now I cannot weak rotate it anymore because the time direction is gone. There's not a single weak rotation which would lead me to a conflict. I hope you understand what I'm saying. For a single brain, I would have a conflict. But the intersection is exactly such that it evades it. It evades, it forbids a Lorentzian continuation. So this, to me, that leaves us very like, okay, nice. This is how string theory gets away with it. And the solution is everywhere, weakly coupled, weakly curved. We checked it, okay? So no problem. Solutions are there. All right. So here is a summary of the state of affairs. In flat space, they're there. We showed it. Nobody should worry. In ADS, I think they're there, but it's just a gauge supergravity description. Would be nice to do better. There's upcoming work on T11, but it's still a little bit unclear. So let me not go there. So at the last part, let me go to holography. Okay. So I showed you, at least we found them in ADS 5 process 5 over ZK, but it was already pointed out that how can this ever work? Holography doesn't show the common alpha parameter, so there must be a paradox. And I agree. And let me go to this slide. So what we have done, okay, is the following. So first of all, let me just remind you, I told you it's geodesics on a sigma model. So let's try to interpret that holographically. This sigma model is a moduli space. The metric on that sigma model is nothing but the Samologikov metric, all right? So interesting, just this simple statement, forget wormholes. We learned from supergravity that geodesics on the conformal manifold correspond to instantons in the CFT. As a field theory statement, it still amazes me, okay? But what do we learn more? So this specific example is the necklace n equal to quiver CFT. And it has like, in the simplest case, you can think of it as K Young-Mills nodes, okay, coupled, but okay, it's not so important. The moduli space in the Euclidean signature, this is Lorentzian, this is Euclidean. I mean, we studied all of the ugly details, and this is what comes out. First, we did it for the SUSY instantons and the extremal ones, and I want to show you that everything works because we get a match with the gauge theory, okay? So what we found, we were able to match the supersymmetric supergravity instantons to the SUSY instantons in the gauge theory. So I know our computations are correct. This was the test case. We can even do it for the non-SUSY extremal instantons. But let me not explain you, I was pretty excited about this, but okay, whatever. Let me go to the wormholes and then I'm almost done. The wormholes are sick. You can immediately see it, like me. They lead to this one-point function. We know that that's impossible. This violates the Cauchy-Schwarz inequality. So there must be something wrong, yet we don't know what it is. Could it be Euclidean stability? I have no time because I only have 1 minute, so let me just summarize the situation. There's lots of literature. We wrote a paper. One of my best friends shows me we were wrong. Thank you, Gary. We agree with Gary. We did a completely alternative calculation. We get exactly the results of Gary. So the wormholes are not unstable. But this was for a single axion wormhole. As I tried to say, the clean string theory embeddings is always axion. My guess, this is a conjecture at the point we're doing the calculation, is that the multi-field case shows the instability. And then the paradox would be gone. Okay, I have no time. Sorry, I wanted to explain the work we did recently also with Gary on the other class, the more physical wormholes in phenomenological Lagrangians, but I don't have the time, so we can talk about it later. So let me go to the summary. Why wormholes are in the landscape and why wormholes are in the swampland. Okay, they're predicted by the axionic weak gravity conjecture. That's an argument for them to exist. They're needed to break global axion shift symmetry, and that's not clear. As we heard, like you can break the shift symmetry already in field theory. You don't need to have gravity, but it's a discussion you can have. We showed there clear and simple string theory embeddings of wormholes. So you cannot doubt it at the level of supergravity solutions at all. The single axion wormholes are stable despite old literature. And the corrections to small single axion wormholes obey the weak gravity conjecture. This is also something Gary showed and we showed recently as well. Why wormholes are in the swampland? There's a beautiful argument by Jake and Kumran. We showed that they clearly violate bounds in ADS-CFT, which you're not supposed to violate. There's no sign of the common alpha parameters in the dual CFT, so it cannot work. But I also think they're unstable with multiple fields. Thank you very much.
Thanks a lot, Thomas, for the effort. Questions?
Thank you. Very nice talk. So for off-shell wormhole configurations, so things that you imagine contribute to the Euclidean path integral but aren't solutions to the equations of motion, it's reasonable to me that they could cancel against more quantum effects because they're not, semi-classical. There's one configuration path integral. There's other stuff. But would you say that if you have an actual solution to the equation of motion that's stable, that in that case you can't avoid alpha parameters? You're forced to have non-trivial ensemble if you have a solution that's stable.
Unclear. So the wormholes that we have seen in low-dimensional ADS-CFT, they are of the first kind. They're not solutions. You could call them constraining sometimes. Okay. Concerning your question, how to interpret the wormhole as an instanton, of course, depends on the number of negative modes, either 0 or 1. Confusingly, Gary found 0, and then we checked, we found 0. This doesn't fit with the tunneling interpretation in terms of a baby universe. So to me, it's very much unclear. So sorry, I cannot answer the question.
No, that's a good answer. Thank you.
Can you elaborate on your fragmentation observation? You didn't have time and you went very fast. And I was just curious what you mean there. You mean brain anti-brain instabilities or something like that?
Very good point. So very quick. So first of all, if you do a brain probe calculation, you take a wormhole and you probe it with d instantons. Okay, supersymmetric d instantons. You see that the action is lowered by sending them away to the other points of the wormhole, where they would actually eat up the charge, so they would kill the wormhole, right? Some kind of Euclidean Schwinger pair destruction.
However, there's a discontinuity at the moment where the pair is created or not. I mean, this is not quite an instability. Would you call it?
No, I'm giving evidence, okay? If you think in terms of black holes, why over-extremal black holes don't exist? You cannot lump together over-extremal particles. The forces don't work out. But if you would, it would shatter apart, right? So that's what you would think. Like analogy with particles and black holes suggests that the dominating saddle points are the ones where you take a wormhole charge minus n and n, you cut it into n pieces, into microscopic objects. Okay, so I'm pretty convinced that that should be the real picture. But even then I'm confused because I don't know how to deal with a single microscopic object. There is no, the notion of over-extremal instanton is simply confusing. String theory doesn't seem to, there's no description. Think of it. How can there be an instanton that contributes more than the d instanton in type 2b? But that's what the wormhole is saying it is doing. But that doesn't make any sense. So it's very confusing. Yeah.
Last question. Well, there's no more questions. Then we thank Thomas again for this big effort. Thanks a lot.